Hey y'all, we're going to pick up where we left off, which is graphing, okay, one of the trig functions. So today we are going to graph y equals f of x, which equals to secant of x. So now let's just kind of remind ourselves of what the reciprocal function is for secant. Would you agree then y equals, oops, this pencil is broken, so let's just use a red pen. So secant of x is the reciprocal of cosine, okay? Excuse me. So whatever you are doing, for example, your calculator doesn't have a secant button, but you can calculate secant value by dividing it, okay, by 1. Okay, so calculate cosine value first, then whatever value you have, take 1 divided by that. That's what it means by reciprocal. So technically, I'm going to show you how to graph secant by starting out with cosine. Okay, so y equals cosine of x. Because we are experts at graphing cosine, so we are going to use cosine first. And again, as you remember, you're going to need 5 inputs. Okay, 0, pi over 2, pi, 3 pi over 2, and 2 pi. The period of cosecant is the same as the period of cosine, because these two are reciprocal function of each other. So 2 pi divided by absolute value of b. Okay. So this is secant of 1x. Since this is a 1x, b is going to be 1. So period of secant is going to be 2 pi. So I'm going to show you how to graph out 2 pi, which is 1 full cycle, 4 pi, which is 2 full cycles. So anytime you're graphing, I'm going to ask you to do 2 full cycles. I'm also going to go above and beyond and do another one on the -1. So this is going to be a -2 pi. So I'm graphing a total of 3 full cycles here. And each cycle has 4 equal intervals. So 4 equal intervals. Okay. If this is from here to here is 2 pi, right smack center is pi. And each one is worth a pi over 2. Okay. So now we're going to do the parent function. Okay, but before we do the parent function y equals secant of x, I'm going to graph out cosine first, because we all know how to graph cosine really well. Cosine of 0 is going to be 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine 2 pi is 1. Okay, so let me just sketch this out using dash or dotted line. So I'm going to go up by 1, go down -1. So 0, comma 1, that's my dot. Pi over 2 staying at 0. This is a normal cosine curve. Okay, so there's nothing special about this except plotting it. And negative side, just repeating the pattern. Okay. So here is, I'm just going to use dash or dotted line or curves here to represent. Okay. So and technically I can go down and this can go down. So that's what I just finished graphing. Okay, so the blue one, it's all of your cosine. Now, but I'm not interested in graphing out your cosine. I'm interested in graphing out secant. And I want to know, how might that look? Okay, so this is going to be my output, which is y equals secant of x. I'm interested in graphing secant of x. This one that we just finished is going to be your cosine of x. Okay, so that blue one. Well, secant is, I'm just going to take the output. Okay, so cosine of 0 is 1. And then whatever I have, well, the reciprocal of 1 divided by 1 is still 1. Right? So check this out. The reciprocal 1 is still 1. Then I'm just going to take 0 and take its reciprocal. Well, what happened when I take the reciprocal of 0? This is now undefined. Well, what's the reciprocal of -1? What's 1 divided by -1? It's actually still -1. And 1 divided by 0, which is similar to pi over 2, is now undefined. And 1 divided by 1 is 1. So check it out. All the outputs for cosine, okay, it's very similar to all the outputs for secant, except, except at 0. At 0, cosine is now undefined at secant. So that means I'm going to start having asymptotes. So I have an asymptote here at pi over 2, because at pi over 2, the output for secant is undefined. Okay. Then I have another 0 at 3 pi over 2, which is this right here. So check it out. Anytime cosine is on the x-axis, secant has an asymptote, because when you take the reciprocal of 0, the 0 becomes in the denominator, and you can't really have that, so it becomes an asymptote. So right now, those are all your asymptotes over 3 full periods. Okay. So the asymptote is part, it's part of the secant graph. So make sure you have it on there. Now, so what does, when x is 0, the output for secant is at 1. So you only have one dot. Okay, there's only one dot. Excuse me. And so let me show you where the second dot is. Okay, and there's an asymptote. We have that right there. When x is at pi, I have a dot at a -1. So here's another dot. Okay, notice how it's at the top. Okay, it's at the top of the cosine function. It's at the very bottom of the cosine function. And when x is 2 pi, I have a dot. The output is +1. I have a dot at 1. So what on earth, what on earth are you supposed to do with those 3 dots that we plotted? Okay, well, we have asymptotes for a reason. And the definition of your asymptote is where the function approaches. And this is going to approach. That means it's going to make a parabola, a nice opening up parabola, because that dot is on the top. And it's going to open down here. So that is 1 full period. Okay, from here to here is the distance, a total distance of 2 pi. Because you have from here to here, okay, that's 1 pi. From here to here is another pi. So total distance-wise is 2 pi. And since I have another dot here on the top, I'm going to make a parabola that's opening up. Okay, and I'm just going to repeat the pattern. Notice how, like, from here to here, that's not a period, because this piece is repeating this piece. So therefore, the period is only, you can say, from here to here. So if I were to calculate the distance, it's a distance 2 pi, or from here to here. Okay, either way, the distance is still going to be 2 pi. Now, does it look like it has an amplitude? Is there like an absolute value of a total height that you can quantify? And the answer is probably not. This is kind of like tangent and cotangent, how it goes up forever. So the amplitude for secant is none. Okay, secant doesn't have an amplitude because it goes up forever and it goes down forever. So since I have an absolute maximum here for my cosine, then you know there's a dot here, and you know there's a parabola that's going to open down. Excuse me. And looks like there's a maximum point here. So I'm just going to do half a parabola here. And looks like there's an absolute minimum here. So I'm just going to go do another dot on the top and have it a parabola. And if you wanted to, you can also do half a parabola right here. But I'm not going to. I'm going to stop right here. So if you check this out, okay, the blue graph is the cosine graph, which I don't really need to graph that out. I was just showing you how they are related. The red one is really what we need to graph, and what you are only required to graph if I ask you to graph out secant of x. Okay. So let's talk about the domain. The domain of the red graph. Okay. It's going to be all real numbers excluding. Notice how it's excluding pi over 2, 3 pi over 2, 5 pi over 2, right? So the domain. Let's talk about. Remember, we're graphing out y equals secant of x, so we're only looking at the red stuff. The domain is, we're going to say, hey, all real numbers excluding, okay, dot, dot, dot in the front. I can exclude the negative pi here over 2. I'm going to exclude the positive pi over 2. I can exclude 3 pi over 2. And then this is 5 pi over 2. Then I can also exclude 7 pi over 2, dot, 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 okay? Well, I can't really sit here and list that out, because that would not be correct. I can't sit and list it forever. So I'm going to need to write an equation. I'm going to use this very first positive number, and check this out. From here to here, it looks like I'm adding, okay? What am I adding? 2 pi over 2, right? because 1 pi over 2 plus 2 pi over 2 is 3 pi over 2. From here over here, I'm also adding 2 pi over 2. But 2 pi over 2 reduces down to a pi. So one of the ways you can write is domain all reals excluding pi over 2. We're going to start with the smallest positive here, plus pi k, where k is any integer. Okay, it can be positive, it can be negative, and once you check, for example, if I want k to be negative 2. So negative 2 times k is going to be negative 2k. Pi over 2 plus negative 2k. I should end up at excluding a value of a negative 3 pi over 2. So here's 1 pi over 2, here's 2 pi over 2, and here is an asymptote at 3 pi over 2, which is correct. Okay. Symmetrical. Symmetry. Okay, does it fall on the y? Is it mirror image about the y-axis? Or is it mirror image about the origin? So if I fold on the y-axis, the left and the right, they fold right on top of one another. And it should also be the same as cosine. Okay, so cosine had an even symmetry. This is also an even symmetry, which if you remember, an even symmetry was f of x equals f of negative x. Remember this? Okay. Oops, there you go. Period, we stated earlier, secant of x has the same period as cosine. X-intercept, does it ever, look at the red and only red, is the red graph, okay? Is that ever going to touch your x-axis? No, it does not. The blue stuff does, but I'm not on part 3 here. We're graphing secant of x. The blue stuff belongs to cosine of x. Okay, so this one does not have any x-intercept. Y-intercept, we have one dot and only one dot at 0, comma 1. Maximum and minimum, we don't have either one because it goes up forever and it goes down forever. Okay, and that's why we don't have an amplitude. So that's what a y equals secant of x looks like. And that's how secant is related to cosine. Now the next one we're going to do is we're going to graph out cosecant. And guess what this is going to be related to? This is going to be related to the reciprocal function of sine of x. So that's what I'm going to do first. I'm going to graph out sine of x first, okay? So here is my input. I'm going to y equals sine of x. Okay? Those are my outputs. So 0, pi over 2, pi, 3 pi over 2, and 2 pi, my 5 inputs. Let's take care of the 5 outputs. Sine of 0 is going to be 0. Sine of pi over 2 is 1. Sine of pi is going to be 0. Sine of 3 pi over 2 is negative 1. Sine of 2 pi is back at 0. So that's my sine graph. And let's try to graph that out. The period for cosecant is the same as sine. So I'm going to take 2 pi divided by absolute value of b. Since this is the parent function, all of your a and b are both 1. So this is just going to become at 2 pi. So I'm going to go a negative on the left, a positive cycle on the right, and another positive cycle. Okay, so I'm going to go 3 full cycles, although you're only required to do 2 each time. And I'm going to have 4 equal intervals here. Okay, so here we go. I'm going to go up at 1. I'm going to go down at negative 1. Alright, so sine is 0, staying at 0. Pi over 2, I'm going to go over 1. Pi, I'm going to be at 0. 3 pi over 2, I'm going to go negative 1. And back at 2 pi, staying at 0. So I'm just going to repeat my dots, okay? Repeat, 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 repeat. Okay, so this is what's called periodic because it continues, it repeats itself. Okay, so I'm going to use, just like the cosine above, I'm just going to use dash or dotted, okay, to graph this. Because I'm not really, part 4 of graphing, I'm not trying to graph sine. I'm just trying to show you how sine is related to cosecant. So that's a sine function. Okay, I'm really interested in graphing cosecant. Okay, so y equals cosecant of x, which is really the reciprocal according to this right here. So what happened when I take the reciprocal? Take 1 divided by the output. 1 divided by 0. What happened when when x is 0? Cosecant is undefined. Would you agree? Okay. Then I'm going to take 1 divided by 1. 1 divided by 1 is still 1. So cosecant at pi over 2 is 1. And we're just going to repeat this pattern. 1 divided by 0, it's undefined. 1 divided by negative 1 is negative 1. 1 divided by 0 is back at undefined. So all the zeros just kind of turns, okay? All the zeros just kind of turn itself into the undefined. So that's what we're going to do now. So here's a 0, okay? When the blue graph right here, which is the sine graph, is 0, you have an asymptote because cosecant is undefined. Here's another sine, 0. Okay? There's another 0 for sine. There's another one right here. And then here. And here. And here. So notice how all of those asymptotes are there. Okay. So the first asymptote's at 0, the next one's at pi, the next one's at 2 pi, 3 pi, 4 pi, and so on and so on. Okay. At pi over 2 though, cosecant is positive 1. So notice how there's a dot at the maximum value of sine. And then at 3 pi over 2, cosecant is negative 1. So here's a dot at the minimum. Well, you have 2 dots. It's going to be very similar to your secant. We can approach your asymptotes on the sides here. And we're going to approach the asymptotes. So that is what's called a one full cycle, one full period. And I'm just going to repeat myself. Okay. If there's a maximum on the sine, that's where my top is going to be on the top, and it opens up. There's a minimum. I make a dot on the top of the minimum, or the bottom, I'm sorry, at the minimum, and then make a parabola. And similarly, so pretty much where sine and cosine has its minimum and maximum, that's where we put our dots, right, for cosecant and secant. And then the parabola opens up or down, depending on if it's on the top or on the bottom. All right. So, domain. Oh, let's talk about amplitude. Do we have any? Is it an amplitude that we can quantify? Okay. As you can tell, it goes up forever and it goes down forever, so there is no amplitude, none. Okay. All right, domain. It's going to be all real numbers, and we can exclude, okay? All real numbers exclude. Looks like this is a negative pi, negative 2 pi. So it's dot, 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 negative 2 pi, negative pi. Here's a 0 at the asymptote. And remember, we're talking about cosecant, which is the red graphs, right? And then this is pi, and 2 pi, dot, dot, dot. Okay, so these are the these are the x values we are excluding from our domain. So how would I, from here to here, I'm adding a pi. From here to here, I'm adding another pi. So technically, if I were to write an equation, I can start with the first positive, or first non-negative, 0 plus pi k. But 0 plus anything is really itself, so I can just say exclude this, okay? So domain is all real numbers excluding pi k. Okay, where k is any integer. Okay. Your range. Oh, you know what I just forgot? I completely forgot. Notice how I completely forgot to write the range right here. The range is going to be from 1 and above, right? And then negative 1 and below. So we're going to write from small to large. Negative infinity to negative 1. So negative infinity to negative 1. Union that with 1 to infinity. I'm sorry. Include 1. It's inclusive at 1. So square bracket. Okay, so square bracket at 1. Alright, because that is going to be the same range for our cosecant down below. I just completely forgot. Alright, so the range is the same thing from negative to negative 1. So negative infinity to negative 1 inclusive. Or positive 1 inclusive to positive infinity not inclusive. Okay. Symmetry is going to be the same as sine, which is an odd symmetry. Okay, an odd symmetry, and based on your first semester, an odd symmetry is f of negative x equal to negative f of x. That's what an odd symmetry is. Period is the same as sine, which is 2 pi. X-intercept, okay, your cosecant and your secant graphs, the two graphs will never ever cross over your x-axis, so none. Y-intercept for this particular cosecant, it doesn't have any. There's no max and there is no min. Okay. Okay. So we have sort of filled out even and odd, okay, for all of your functions, all 6 trig functions. Now the question is, let's put it together. Okay, so that way you have it all in one spot. You have 2 functions that are even. Okay, so let's talk about those first. You have your cosecant. So your cosecant is even. That means you can have a cosecant of a positive angle is the same as cosecant of a negative angle. That's what it means to be an even function. Well, then the reciprocal function of this, is secant. So secant is also an even function. Okay, so let's just write even. So secant of a positive angle is identical to secant of a negative angle. So for example, cosine of 45 degrees. We all know, or hopefully we all know by now, that's rad 2 over 2, which is the same thing as cosine of a negative 45 degrees. Okay, because negative 40 degrees is right here, and positive 45 degrees is right here. Negative 45 degrees, positive 45 degrees. Okay, x is positive in both quad 1 and quad 4. So that's why both of these are even functions. The rest of these are odds, okay? Odd, 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 and odd. And what does it mean? So let's talk about sine. Okay, sine of a positive 45 degrees is not the same as sine of a negative 45 degrees. So positive is it's on the top, and that's sine of positive 45 is positive. Sine of negative 45 is negative. So in an odd function, sine of a negative 45 degrees equals to a negative sine of a positive 45 degrees. Okay, so notice how sine of a negative 45 degrees is a negative rad 2 over 2. And then if I were to go and, hey, just find sine of positive 45 degrees for me, which is a positive rad 2 over 2. But I want to multiply to negative 1, so to make these two equal. So the reciprocal function of sine is going to be, oh, you know what? Don't write 45. I want to write a generic. Can you just write theta? Thank you. All right. The reciprocal function of this is cosecant of a negative theta equals negative cosecant of a positive theta. Okay. Oh, sorry. Don't do bubble, because I can also have radians. Ignore that. I should get a pencil. Okay. Another odd function is a tangent. So tangent of a negative theta equals to negative tangent of a positive theta. So how is it going to be useful? It's going to be useful when I give you a negative angle and you don't want to deal with the negative angle, then you can just plot the negative, right? Because these two are equivalent. So tangent of a negative, let's say pi over 6. Okay, and if you don't want to deal with a negative pi over 6, you could just write, hey, that is the same thing as a negative tangent of positive pi over 6. That's all that is. All right, cotangent of a negative angle equals negative cotangent of a positive angle. So you can always change a negative angle from all of these to a positive angle if you want to deal with if you don't want to deal with the negative angle. Okay, there's nothing wrong with a negative angle. Just give you more options. That's all. All right. With that said, I want to stop right here. Oh, actually, I want to pause it right there. Stop right here until our next video.